Hi everyone, welcome to this lecture. So in this lecture, we will learn another important technique which is known as gradient descent in order to reduce the error and to find the optimal value of bias and weights. We have already learned another technique which was least square method. We used least square method to reduce the error and calculate the optimal values of bias and weights. So why we need gradient descent if we have least square method? So there is a potential issue with least square method that we have to calculate the inverse of a matrix. There is a matrix known as xt multiplied by x, and we calculate the inverse of this matrix when we apply a least square method. Now there arises a situation in which inverse is not possible. That is, if x transpose x is not of full rank. Full rank means that the magnitude of x transpose x should be possible and all the columns are independent. If this is not a case, then x transpose x will be a singular matrix and its inverse will not exist. In that case, we cannot apply least square method to reduce the error and to find the optimal value of bias and weight. The other requirement for least square method is that the number of samples should be very large than the number of features D. For instance, if we have 50 samples in our data and we have 5 features, in that case, n is not very large as compared to D. In that case, there might be a problem with applying least square method. So for solving these two issues, we have another method known as gradient descent. So how to reduce error by gradient descent? So we know that error is the difference between the targeted value and the predicted value. So this is our first step. First, we need to calculate the error. After that, we need to transform this error into a mean square problem. So this is our error, and this is the transformation of error into mean square error. Now, this is our error. Here we are squaring the error, and here we are taking the mean by adding the square error and dividing by the number of samples. So we have transformed the error into mean square error, and then we will apply gradient descent in an iterative way. So basically, when we will implement in Python, we will use a for loop. In that for loop, we will run it again and again, and with every iteration, the error will be reduced and the weights and biases will be updated towards the optimal value. So this is the iterative optimization algorithm. Now, the next step is that we have replaced ypred with the product of x and w. If I go back, this is ypred. This is the predicted value, and we know that this value is equal to the product of our feature matrix and weight matrix. Now, this is a loss function which we have been used previously, and now we are using gradient descent to find the minimum value of the loss, or we want to update the value of weights and bias. So the first step is to take the partial derivative or gradient with respect to w. So basically, if we see this equation, we have three variables, y, x, and w. Since we want to update the weights, therefore, we will differentiate this error equation with respect to w. So that differentiation with respect to only one variable will be known as partial derivative or the gradient. So here I am taking the derivative of this equation with respect to w. So here is a square on the whole bracket. So according to the chain rule of a differentiation, first we have to use 2 here, then y minus xw, and after that we have to take the derivative of the terms which are inside this bracket. So since we are taking the derivative with respect to w, so this y will be a constant. So the derivative of a constant is 0. So here we did not write 0, then there is a negative sign, and the derivative of xw with respect to w is only x. So that was the first step where we have calculated the partial derivative. Now the second step is to rearrange the terms. So we have 2, we have n, and we have this negative sign. So we move negative sign to here with the n. So we have minus 2 over n, and rest this x, we will write it first, and then we will have this bracket y minus xw. So this term where we take the derivative of our error with respect to w is known as gradient. After calculating the gradient, we need to update the value of the weights. So this is the equation to update the value of the weight. This is our old value of the weight. This is gradient. So we will multiply the gradient with an important parameter known as learning rate or a step size. We usually call is learning rate. So we will multiply our gradient with this learning rate. Then we will get a term. We will subtract this term from the old weight and we will get the value of a new weight or the updated weight. So this alpha is known as learning rate. So what is the importance of a learning rate and what is the definition of a learning rate? So basically learning rate controls how much the value of weight changes with each step. So the value should be small, such as 0.01 for good training of the model. So it controls the amount of learning or amount of updation of the weight value. So we need to set it small so that weights learn slowly and reach to the optimal position. So let's understand the concept of learning rate or step size more with the help of a figure. So this is the pictorial explanation of a gradient descent. We know that our mean square error has a convex shape because there is a square on the error. And in convex shape, we have a global minimum value at a particular point where the slope of the curve is 0. So here we have a slope and here we have a slope, but this is the point where slope is 0 and here we have to reach. So where there is a slope, where slope is 0, at that point, the value of error is also 0. So what we will do, we will start from here and we will move slowly towards our requirement or our target. This is the goal or the target of gradient descent. So we take small steps. So that step is called learning rate. So we keep on moving slowly and slowly until we reach our goal or until we reach our target. If we take large step, so there is a chance when we reach close to the minimal value, we may exit from that value or we may miss that value and we reach to the other side of the slope. So the important concept is the learning rate should be small, or learning rate is also known as the step size, or a step size should be small so that we can slowly and slowly move towards the minimum value. Sometimes it happens that we set the value of learning rate high at the start. So we take large step at the start, and when we are close to our goal, we take the small step. So what will happen if we take the large step throughout the iteration process? So in that case, there is a chance we may miss the global minimum position, that we are here and then we take a large step and we miss the global minimum value and we move to the other side of a slope. In that situation, if we take the large step or if we put large learning rate, we will keep on vibrating around our target value and we will not be able to reach it easily. So this is the importance of step size. That's why it should be a small value, that is 0.01 or close to 0.01. So here is some comparison between gradient descent and least square optimization method. So it is an iteration process. We have to iterate it over again and again by using a learning rate, and then we have to update the weight after every step or after every iteration. So there is no iteration involved. We know that we construct matrices in least square optimization, then we multiply the matrices, then we take the inverse, and finally we get our optimized weight. So there is no iteration. So there is a learning rate. Now this is a very important parameter. If we do not select the learning rate well, we will not get the optimal performance from our regression model. So learning rate is another challenging thing in gradient descent optimization. Here there is no learning rate. So gradient descent also works well from small as well as large value of data samples. So we know that if the data samples are small, we can apply gradient descent as well. But there is a potential issue with least square optimization. There are two issues. The first issue is that this inverse should exist. The second issue is if n is too large, the process will be very slow. Furthermore, if x transpose x becomes singular, inverse will not exist. So the problem is that the inverse should exist. And the other thing is, if the number of samples are too large, then it will be a slow process. So these are the few comparison of gradient descent and least square optimization. So I hope you understood this lecture on the importance and the working of gradient descent algorithm. Thanks for listening, and I will see you in the next lecture.